molecular vibration and rotational levels. And they have like very different energy scales, so you can imagine in an additional way with respect to neutrons. And the nice thing is that you can envision completely different new protocols where you can, for instance, exchange quantum information with these polar molecules, or also use these internal degrees of freedom to do physics that is beyond the standard model, like as it is being recently demonstrated by the Harvard collaboration and Yale collaboration for measuring the electron-electric dipole moment. Like highlighting again, like how powerful these tabletop experiments are with respect to the distance and into the probing of like beyond standard physics, standard model physics. The key, you want to prepare this molecule into a unique initial quantum state. So it's very important to have like translationally cold temperature. Ideally, you want this temperature to be in the ultra-cold regime. All right. For the sake of this conference, polar molecules are interesting for the type of interaction that they have. So molecules can have a dipole moment if they are immersed in a biased electric field. Is it working? Sort of. Okay. And this interaction, okay. Okay, can I go? Okay. So they have anisotropic long-range interaction. So they can tune with a biased electric field. And in principle, you can put this polar molecule into an optical lattice. And because of these additional degrees of freedom that you have, you can realize exotic phases of quantum matter, like topological superfluids, strongly interacting lattice spin mode, and so on. And the key advantage is that this term in the interaction already pops out into the Hamiltonian. Okay, sorry. Okay. Cell phone away. Okay. Now it's better? Okay. So this interaction already pops out at first order in the Hamiltonian. And this is going to increase like the critical temperature where you're expected to see all these exotic phases. Still, you need the polar molecules to be in a quantum degenerate regime. So you need the filling, naively, to be very large inside the optical lattice. All right. The state of the art for the production of ultra-cold polar molecules is represented by making these polar molecules out of a mixture of bialkali atoms. And in particular, in our experiment at GIRA, we use a mixture of potassium 40, which is the fermionic species, and rubidium 87, which is the boson. This mixture features like a heteronuclear flashback resonance at a field of 550 gauss, where we can exploit to associate coherently free atoms into flashback molecules. These molecules are very loosely bound, so they have essentially no dipole moment. And in order to induce a dipole moment into the molecule, we coherently transfer these molecules using a stirrup, which is short for stimulated rapid adiabatic passage. We use like a two-choro transition that brings the flashback molecule through, climbing through the intermolecular potential to the absolute ground state. And this difference in the two photons is about 6,000 Kelvin. So the preparation has to be carefully managed in order not to heat up the molecules. And the recipe that we use for making this molecule, the recipe that we use for making this molecule has been pioneered back at GILA almost 10 years ago. But the bottleneck of this approach is that the flashback molecule creation is very poor. Like essentially it's like 20% efficient, to put a number. And this makes the final sample that we can create, or they typically create around a factor of 1.5 above TF, something like that. So still far away from the quantum degenerate regime. So now we have a new machine at Gila, and the solution to this problem to make the polar molecules quantum degenerate has been to use brute force, essentially, on the part that we already know how to handle pretty well, so laser cooling and evaporative cooling on the atomic side of the experiment, so before making the molecules. And the key ingredient has been the implementation for both the two species of what back days was called velocity selective coherent population trapping. Now people call it gray molasses. And it turned out like it's well established that now it's very beneficial for potassium because potassium lacks of hyperfine definition in the excited state. And so impossibility of having sub-Doppler cooling, but it's also very important for rubidium, which usually people use conventional sub-Doppler cooling mechanism. And we typically end up with a sort of like 1 million of atoms in each species at a temperature around 250 nanokelvin. And the highlight of our new experiment is represented by this chamber on the right. So we have a tiny glass chamber that in principle has a lot of numerical aperture. So since the experiment is not complicated enough, so we can also try to implement quantum gas microscopy, but probably this is farther away. And the key part of our experiment is represented by this stuff that is placed in vacuum inside the chamber. And this is a combination of the electrodes, a set of electrodes, so two ITO plates on the outer side, and 4 rods that can be used to induce like a large bias electric field, or even gradients in every direction. We can use to tilt the electric field inside the chamber, and also we can use it to produce microwave fields. Okay, so the starting point, as I was saying, is represented by the atomic side, and we can typically produce like very different mixture, and in particular at very different degrees of degeneracy. So this was the condition that I showed up before, where we end up with sort of 1 million of atoms at each species above 200 nanokelvin. But then by adjusting the experimental parameters, in particular about the trap loading for potassium, the final optical evaporation cut, we can end up with a mixture that is extremely degenerate, where we have somehow 500,000 of atoms for potassium at a temperature around or below 0.1. And then inside this mixture, there is like a rubidium BC that is also extremely condensed, so the thermal fraction is pretty small, with an atom number around 70,000. This is probably an interesting mixture also for boron physics and so on. But the key idea that we have now to produce like degenerate molecule is to transfer the high degree of degeneracy from the BOSE Fermi mixture in the most adiabatic way as possible into the molecular sample. So starting from this mixture, we do all the steps like Feshbach resonance association through a sweep in the magnetic field, and then coherently transfer to the absolute ground state, and hope that the initial low entropy is then transferred in a sort of equilibrium way to the molecular gas. Okay, so we end up typically with this picture. After we transfer to the ground state, we take out all the atomic components, and then we bring the molecules back into the Feshbach branch. So we take conventional absorption images onto the CCD, and the numbers that we obtain are typically around 30,000 molecule, temperature of tens of nanokelvin. And this gives us like from, you can see this azimutally average radial profile through a feed through the Fermi-Dirac distribution. You can see that the T over TF is around 0.31. So this gas, this feed has no residual, as it was showed by almost 20 years ago by Brian DeMarco and Debbie Jean, always at Gila. And as we feed the same cloud with a classical feed, you can see that the feeds overestimate the density at the center, and the residual as the typical flipping side. So ripples in the residual that go as you move away from the center of the cloud, that are the hallmark of quantum degeneracy for the fermionic species. And if you want to extract correctly the temperature of this system with a classical fit, you can also see that constraining the fitting function always only at the edge of the density profile gives an overestimate at the center. So this is, again, another signature. And so this is an ideal Fermi gas, and one way to see if it's like another way to translate this happening of the degeneracy is to estimate like the Fermi energy that is associated into this harmonic shaft. Because fermions, even at zero temperature, have a finite energy that is given by the Pauli pressure, by the Fermi pressure. And similarly, again, to what was done 20 years ago for the normal Fermi gas, for the, atomic Fermi gas, you can see that this excess energy increases for both the potassium-40 and the molecules, which are the purple point, increases as we lower the degree of degeneracy, and in theory should grows to 0.75, something like that, of the value of the Fermi energy. And this again is telling us that our gas is a sort, again, even if it's composed of a extended object, is an ideal Fermi gas of fermion. Okay, so one benefit that we have from making this molecule into this setting is that we have an extremely large Fermi gas, and only at the center we have an impurity. So an impurity that is represented by this boson. And we expect, based on quantitative determination of the Fermi temperature and so on, so essentially going from the trough frequency to the atom number that we have, an increase of the T over TF by a factor of 4 when we go from the atomic component to the molecular component. But because the BEC is only present at the bottom of the trap, so the BEC is extremely condensed, so it's essentially localized at the trap bottom, the entropy of the potassium that is around the rubidium cloud is smaller. And so this translates in an increase of the degree of degeneracy once we make the molecules, and we typically have something of just a factor of 3 below what we expect. Just a factor of 3 above what we created initially for potassium. Another nice feature of this configuration is that the peak density of rubidium is only about a factor of 2 or 3, and the bad mechanism in the association of Feshbach molecule while we cross the Feshbach resonance is the 3 body losses of 1 potassium and 2 rubidium. And since we are in this impurity regime where the rubidium number is reduced significantly, so we are in usually a ratio of 10 to 1 of potassium to rubidium, this mechanism is essentially suppressed. And so we can convert a lot of rubidium atoms into molecules. So the conversion efficiency of rubidium atoms over the number of molecules is about 50%. Of course, the bad side is that in this regime, the conversion efficiency for potassium is terrible. It's like way below 10% because most of the potassium cloud doesn't see the rubidium. All right. Okay, so another nice feature, let's say, of the molecules is that even if they are ultra cold, undergo chemical reaction. And in particular for KRB, even if it's in the absolute ground state, it is possible that when 2 molecules touch each other and come a short distance, this molecule dissociates. So there is a chemical reaction that releases an amount of around 15 Kelvin. It's an exothermic chemical reaction. And the two initial polar molecules are converted into 1 potassium molecule and 1 rubidium molecule. So the reaction is so strong that essentially what happens is that the molecule, once they interact, they are instantaneously lost from the trap. So a nice feature that we have for free is that since this is an ideal Fermi gas, the lowest available collisional channel is the P wave one. And so this gives us the interaction potential, the intermolecular potential in this case, as a centrifugal barrier that kind of stops the molecule to approach each other. However, the molecule, according to their energy, they can tunnel from the outside of this barrier to the inside. So you really have to think about this barrier as like a volcano crater. Once the molecule get inside, they cannot escape anymore. It's like there is like a sort of black hole that heats up the molecules and never releases them. And usually the reaction rate so follows like a P wave relation. So the tunneling probability to go from the outside to the inside follows like a so-called Bethe-Wigner threshold law, so it's proportional to the kinetic energy, hence the temperature. Okay, so to put this like in a better formalism, this chemical reaction happens between two molecules. So when two molecules touch each other, and this results in a change over time of the density of our molecules inside the shaft. And this is parameterized by this first lossy term in our system, which is a two-body decay, which is proportional to the reaction rate, that in our case, as I told before, follows the P wave laws of collision, so it's essentially like has a linear dependence of temperature. And moreover, since we are in a trap, there is going to be a rearrangement of the density. There is going to be a volume change, temperature change inside the trap. So we have to take into account also a temperature change of the molecules. This is usually called anti-evaporation, but in our system there are also like different sources of heating that comes from the optical trap and so on. And what we see in the experiment, so we do an approximation in order to solve this differential equation and fit chemical reaction in our system, we have to assume that the temperature increases linearly. In this way, when we put this thing in Mathematica, we can have like a fitting formula. Okay, so this is like a typical trend of the reaction rate that goes on, so how the density changes as a function of time for two different set of temperature. And as you can see, for like very hot cloud, there is a super exponential, so the decay is beyond the exponential decay, is a two-body decay, as I was saying. Instead, when we reduce the temperature, the reaction rate is softer. Like the reaction happens on a longer time scale. The nice thing that we can do now is, of course, we can change the temperature and see how the reaction rate goes as a function of this. So the y-axis on this plot is a logarithmic scale. And the line here, the red line, is the prediction for the P-wave channel with the B coefficient that I was talking about coming from this multi-channel defect theory by Paul Julian and collaborators. And you can already see from this plot that the data like arrange according to two branches. So one set of points are very close to this trend, to this line, and a set of points that is deviating, essentially, from of the P-wave collision. And the nice thing results in the fact when we realize that the different behavior along this line happens as a function of the T over Tf of this molecule. So for molecules that have a temperature or like a degree of degeneracy above 0.6, they really very well agree with the prediction for the P-wave theory. Instead, when the degree of degeneracy is significant, so well below 0.6, the deviation from this prediction from the P-wave collision starts to be extremely strong. Of course, so we can now plot this B coefficient, so essentially we divide the chemical reaction rate over the temperature, and you can see that it's a very nice plot if we plot it on the x-axis now as a function of T over Tf. So this is on the uppermost corner, the same data from before, and then when it's plotted against the T over Tf, you can see that the reaction rate or the reaction coefficient is flat for the red data point with an average value that is very well in agreement with the prediction for the from the defect theory, and instead when the degree of degeneracy increases, the reaction rate drops a bit, like a factor of 4 or so on. And is like the question that now we ask ourselves is that there an effect that is directly related to the Fermi degeneracy that is affecting the density, which is the main mechanism for the happening of this chemical reaction. And of course there is, like this mechanism is what is typically called for ideal Fermi gases, suppression of density fluctuation. There are other ways to see this, like anti-bunching and so on. So essentially when the Fermi the levels of the harmonic trap are filled, like it's very difficult for the fermions to come a short distance. So there is an additional repulsion that is, in our case, also stabilizing this chemical reaction. And so this is a very well-established theory for trapped Fermi gas. So we kind of now try to put this theory on top of the experimental data. So these are experimentalists trying to do theory. So we essentially multiply the average at IT over TF by the fluctuation that we get in the Fermi gas. Of course, like a complete theory has to include more complicated scenario. The kind of data we want to show is that we have like a qualitative agreement with the experimental data. All right. And in my final slide, so I will want to give you a sense of the things that we are trying to do right now. And the goal is to make like Fermi gases of polar molecules even colder. So with the condition that we typically have right now, we can, with these Fermi gases that are T over TF of about 0.3, when we will eventually load like this molecule into an optical lattice, we will reach like a filling of 0.3 maybe, which is above the psychological value of the percolation theory that people is interested in the disorder community. The idea is that we now want to use also control the elastic components of the interaction. And this is usually achieved by polarizing the molecule inside an electric field. So as you can see, without an electric field, there is no dipole moment. So the interaction of this molecule is isotropic. Instead, when we polarize them inside an electric field, along the direction of the electric field, the attractive part of the dipolar interaction comes in and lowers the barrier, the P-wave barrier. Instead, this is the so-called head-to-tail collision. Instead, on the side-by-side collision, which is the radial direction along the perpendicular to the electric field, the repulsion is increased. Of course, this configuration is extremely bad since we are making the collision in one direction barrierless. And so the molecules can come a short distance and react even more. So the trick that was also found by Marcio, who should be here in the audience, like 7 years ago, is to put this molecule inside an optical lattice that is aligned parallelly to the electric field. And in this way, the head-to-tail movement is suppressed. So the molecule, the chemical reaction should be stopped along this direction. And in principle, once there is like an elastic or like an increase of repulsive part in this barrier, you can eventually apply like a electric field gradient along the layers of your optical lattice and spill out molecules. And if the elastic component is enough, you should be able to increase phase pair density a bit further. So this is a sort of preliminary data that dates back to this set of literature and this paper by Marcio and collaborators. So you can see that in 3D, when you put the electric field, there is like a shoot off of the chemical reaction. But instead, when these molecules are put inside an optical lattice, you have like a soft spot, like a regime where the chemical reaction is kind of stabilized. And so you can really exploit the elastic collision in this system to try to eventually evaporate a bit further. And this is like something that we are trying to pursue right now. So the key part of this slide is that it's extremely preliminary. And what we are trying to characterize is the increase of the phase space density. So this is a very old school criterion to check if the evaporation is efficient in our system. So one says to see that the atom number that you have in your system is not changing so much as a function of temperature. So essentially, if you're losing preferentially more atoms rather than diminishing the temperature, you're not increasing phase space density. And the number that you have to care for is the dimensionality of your system, so this D capital. So in 3D, the evaporation trajectory of your system has to be lower than 3, which means essentially you're not losing atoms and increasing, you're just increasing phase space density. In 2 dimensions, it's a bit more complicated. So the slope that you have to achieve has to be lower than 2. Essentially, the difference that you're evaporating out of a disk instead of a sphere. So the space is reduced for this increase of phase space density. And this is extremely preliminary again, but in the regime where we don't have a biased electric field, so essentially no dipolar interaction, we see that when we try to evaporate, so we put a gradient parallelly to the disk, we see that of this evaporation trajectory is negative. So we essentially are just losing atom number and increasing in temperature. So the time here is going like this. And this is extremely bad. So this is showing again the inelastic dominated processes typical of polar molecules. Instead, when we try to increase the bias electric field, we can see that the slope changes from negative to 2. So still, again, we are not increasing phase space density, but here, when we go to the induced dipole moment of around 0.2 dBi, we can see that the slope of this system becomes smaller than 2. And so we are actually increasing phase space density. And ideally, the goal is to have, like, in the further future, a gas with a T over TF below 0.1, with a unity filling that we hope is going to be close to 1, and that in particular is going to be tunable. Okay. So with that, I would like to conclude, and also to thank all my other collaborators, Luigi, Kyle, Will, Jake, that has already left, has now moved to Caltech, and June, who is the PI and supporting all of us. So thanks, everybody, for your attention.
Thanks a lot. I'm sure there are questions. Of course.
This is very quick. Is there a relation between rigidity